Hello, everybody. I would like to round out our general introduction to the stars by talking about the ones that don't really fit the mold. So far, we've been talking about stars and their properties, and we've been operating under the assumption that those properties are always the same. They are constant for at least the main sequence part of the life of a star. However, that's not true for all stars. Some stars are sort of the troublemakers where they change their properties with time and over relatively short timescales on the order of days to weeks. These stars that are varying their properties are very appropriately called variable stars. And I want to end our discussion by taking a look at that and actually making use of some of these variable stars by looking for patterns that can tell us something. And really what they're going to do is they're going to give us one of the more powerful ways to determine very large distances here in our local universe. So let's go ahead and dive into variable stars, the ones that change their properties. So I have right here, just on this introductory slide, we have an animation of what's going to be called a Cepheid variable, where we'll focus our discussion today. And you can see that it's changing its properties over time. Over here, you're looking at a light curve of this, which is just how bright it is measured in magnitude over here. So smaller numbers are brighter, and that is getting dimmer with time, and then brighter with time, and then dimmer with time, and then brighter with time. So it is changing its properties. So it's changing not only its luminosity, its radius, but also its surface temperature slash color. So let's go ahead and dive in and see if we can make some rhyme or reason and understand what these stars are. So most of the time, and for the majority of everything we've talked about in Unit 2, Part 2, we've talked about main sequence stars, which are in a lovely hydrostatic equilibrium where gravity pulling in and thermal pressure pushing out are in balance. So the star remains in balance, it remains stable, and it doesn't really experience changes over timescales except for billions of year timescales. However, if you just start looking around at all the stars, and here we're actually zooming in on a star in the Andromeda Galaxy, and you can see that this star right here over the course of days, so December 17th, 21st, 30th, and 26th, this is in 2011, you can see this star is going from dim to brighter and brighter and brighter. This star is becoming more luminous on the timescale of days. It is varying its luminosity over a short time period. Stars that vary their properties, usually the property we're looking at is brightness, because that's just looking at the stars is the easiest way to find it. But stars that do this, we call variable stars. And they are changing their properties, temperature, luminosity, radius, not really changing their mass, really, although sometimes they shed a little bit of mass during these processes. We'll get to there later. But they're doing this over days, months, to years, not on cosmic time scales of hundreds of thousands to billions of years. We're talking about like in the time of a week. So by next week, you could have a star that could brighten significantly. And then the week after, you go back to dim. And then the week after that, it'd be back to bright. So pretty easy to observe this variability. And while a lot of variable stars, there's not a lot of rhyme or reason to their changes and their properties. We'll go with luminosity, so we only have to talk about one of them. But for a lot of them, these changes are periodic, which means they cycle through the same set of variations of to a certain amount of faintness, to a certain amount of brightness, to a certain amount of faintness, to a certain amount of brightness, to a certain amount of faintness, over and over and over with the same time period. A very well controlled situation. So we say that their variations are periodic. And it's these periodic variable stars that really offer us something powerful. Because often, and the ones that we're going to focus on, the so-called Cepheid variables, their period of variation, how long it takes them to go from their brightest to their dimmest back to their brightest, is strongly correlated with the average luminosity of the star, how bright the star intrinsically is, its natural brightness, which is going to give us a way where we don't have to rely on stellar parallax or spectroscopic parallax. We'd never have to take a spectrum. All we have to do is look at one of these stars just over the course of a couple of days, measure its, say, periodicity, how often its luminosity changing from bright to dim back to bright. And if we know the relationship with that with absolute magnitude, then we have the absolute magnitude of the star like that. And if we have the absolute magnitude, then and the apparent magnitude, because that's just looking at it, then we can calculate the distance. No need for stellar parallax, no need for spectroscopic parallax, a different way to get distances. And this is a very robust way. This was really established and it revolutionized our understanding of the universe and astronomy. In 1908, Henrietta Swan Leavitt discovered that there was this very, very, very strong correlation between a certain type of variable star called a Cepheid variable. And I know that is a crazy looking word, but it's pronounced Cepheid. So the Cepheid variable has a very nice pattern between its pulsation period and its intrinsic brightness, its natural brightness, its absolute magnitude, which is really the same as saying its luminosity. So this is just going to give us a way of observing one of these Cepheid variables. We'll observe how bright it is as a function of time, what's called a light curve. And we'll notice that it goes from faint to bright, back to faint, back to bright. So from its brightest point to its next brightest point, and notice that it's the same pattern over and over and over again. Yeah, say this one has a period of 5.4 days, and that period of 5.4 days will map to a Cepheid variable that regularly cycles between a absolute magnitude or a magnitude of 3.6 to 4.3. That's a lot of details, but there is a strong map between the period of the cycle of brightness and how bright it is. And so Henrietta Leavitt didn't do this with just one star. She actually studied thousands of stars in a nearby neighboring galaxy, a satellite galaxy of the Milky Way, the Large Magellanic Cloud. And it was through this, looking at lots and lots of these variable stars, that she was able to discover this relationship. So this relationship between the absolute magnitude and the pulsation period is called the period luminosity relationship, and it is a very strong correlation, which means if it's a strong correlation, there's not a lot of error involved with it. If you can measure the pulsation period, you can get the luminosity. That's practically how we're going to use it. We're going to go say, look at this, look at a Cepheid variable, and it could be one in our galaxy, it could be one in a neighboring galaxy, it could be one in the Andromeda galaxy, and we can do this for pretty much Cepheid variables that are in our local group of galaxies. So we're getting to huge distances here. Just go out there, look at these, find these Cepheid variables, measure the period of variability, and use this period luminosity relationship. And now we have the luminosity. And that's what this is showing right here is the x-axis is the pulsation period, how long it takes to go from bright to dim, back to bright. And notice that it goes all the way down to about 1 day for Cepheid variables to about a month. And then the intrinsic brightness, the absolute brightness, the luminosity of the star. And it's a nice strong relationship. So if you determine the period is 3 days, and you can go up here and it would have, say, about a luminosity of 8 to 900 solar luminosities. So a very easy way and a very powerful way that works for very large distances to measure the luminosity independent of any other factor. All you have to do is look at the star. You don't need to do a parallax measurement, and you don't need to look at the star's spectrum. So any object in the universe where we can independently determine its absolute brightness, its luminosity, we call a standard candle because it's a way to get a standard brightness. We know how bright those stars are naturally, regardless of whether or not we know their distance. So if we can just see how bright they appear, then we can actually calculate their distances. So these standard candles are a holy grail of astronomy, identifying them, because they'll give us a way to determine the distances to the stars. And what's incredible about these Cepheid variables is that we can identify them in galaxies that are millions of light years away. I mean, spectroscopic parallax is great, but you need to actually be able to take a spectrum of a star, which limits how far away that star can actually be. And you can actually get a spectrum to do a spectral classification and a luminosity classification. These Cepheid variables, they can be seen for millions of light years away. And we just have to measure the period of its luminosity variability, the brightness variability, and we can extract how truly bright it is. Then use the distance modulus to calculate the distance. And we do this with the Cepheid variables to map out our local group of galaxies and even a little bit further beyond. And this is the first time that allowed Edwin Hubble to come along and use the results of Henrietta Swan Leavitt to actually measure how far away galaxies are and see that the further away a galaxy is, the faster it is receding from us, by also correlating that to a Doppler shift to see that our universe is expanding. All right, so we now talked about several ways to get distances. And this allows us to start building, or most of the rungs, of what astronomers call the cosmic distance ladder, the astronomical distance ladder. And it just summarizes all the methods that astronomers use to determine distances in the universe. And the further up you go, the higher the rung on the ladder, the larger the distance you're talking about. So we didn't really talk about this one. It's more in the Astronomy 151 class. But one of the ways that we determine distances in our solar system, one of the most reliable ways, is just radar. Shoot a radio wave at, say, Venus from Earth. That radio wave will bounce off Venus and come back, use the speed of light. You know how fast it was traveling to get to Venus, and it bounced and came back. So you know how far it traveled, you know how fast light travels, you can calculate the distance. So that's what we use within our solar system. But the next rung on the ladder, so to get us outside of our solar system, for nearby stars up to about 10,000 parsecs or so, we use stellar parallax, where we measure the apparent shift of a star from one side of Earth's orbit to viewing it on the other side of Earth's orbit, stellar parallax. And that got us out to, say, nearby stars in the Milky Way galaxy. Then we had spectroscopic parallax using our knowledge of the HR diagrams, which can get us out to about an order of magnitude larger, about 100,000 parsecs or so. So we can map out the Milky Way and things near to the Milky Way, some of our satellite galaxies. And now with Cepheid variables, we can map out to 10 million parsecs away. Pretty far away, 10 million parsecs. And we use Cepheid variables to do that. So that's the next rung on our cosmic distance ladder. And now we are doing some pretty significant things. We are using this period luminosity relationship of Cepheid variables to determine distances to nearby galaxies. How far away is the Andromeda galaxy? 2.5 million light years. How do we know that? We measure Cepheid variables in the Andromeda galaxy to determine the distance. And then we won't actually get there in this class. There are two more rungs to the ladder. There is a relationship between how fast galaxies rotate and the absolute magnitude of that galaxy, or at least for spiral galaxies. That's called the Tully-Fisher relationship. And that allows us to map out to 10 to the 10 parsecs, 10 billion parsecs. And then our last rung is Hubble's law, which I'm sad that we won't get to in this class. I encourage you to look it up, but it's based on the expansion of the universe itself. And it can basically give us the distance to anything we can see if we can measure its recessional velocity. All right, so that ends Unit 2, Part 2 on the stars. Next, we go into what lies between the stars, and I'll see you in those videos.